When you think about mechanical engineering, you probably picture physical prototypes, really complex simulations, and just a ton of hands-on work, right? Well, that world is changing, and it is changing fast. Today, it's all becoming data-driven, and it's being powered by the frankly incredible capabilities of machine learning. So let's dive into what this revolution actually looks like. To really get a handle on this shift, let's just start with a simple question. How would you design the perfect bicycle? I mean, you think about the materials, the aerodynamics, the weight. You'd probably sketch out a few ideas. But what if there was a totally different, a better way? Well, here's the twist. You don't design just one. You ask an AI to dream up thousands of options for you. And no, this isn't science fiction anymore. This is the new reality for mechanical engineers, and it is completely flipping the script on how we create, test, and perfect the world around us. And that brings us to our first big idea, thinking of the AI as a virtual draftsman. This is all about using machine learning not just to analyze stuff, but to actually create it, turning a simple set of rules into a whole bunch of instant virtual prototypes. The key technology here has a name. It's called generative design. And look, this isn't about an engineer just handing off their job. It's more like they become the director. They give the AI goals like, okay, make it lightweight, or it has to withstand this much force, and use this specific material. The AI then becomes the world's fastest brainstormer, exploring literally every possibility you can imagine. So this workflow, it really shows you the partnership in action. First, the engineer lays out the rules of the game. Then the AI, using these really powerful models like variational autoencoders, spits out this massive library of designs. Some look familiar, but some look totally alien, and also happen to be super efficient. And that's when the engineer's expertise comes right back into play to refine and select the absolute best options. It's the perfect blend of raw computing power and human intuition. And trust me, this is not just about bicycles. Not even close. We're seeing these same ideas used to generate these optimal, almost organic-looking shapes for 3D printing using models called GANs. That's where you basically have two AIs battling each other to create the best, most realistic design. It's also being used to design incredibly complex nanolubricants, and even to do inverse aerodynamic design on something as critical as a 3D turbine blade. The creative potential here is just staggering. Okay, so machine learning can help us create. Fantastic. But what about testing? This brings us to the second major shift, using ML as a kind of engineer's crystal ball to predict performance before a single part is ever actually made. The key concept to understand here is the surrogate model. Think about those traditional engineering simulations. They can take hours, sometimes even days, running on a supercomputer. A surrogate model learns from all that complex data and builds a lightweight, lightning-fast version of it. It's like having a fast-forward button for your most complicated tests, letting you get answers in seconds, not days. So what does this actually let us do? Well, it allows us to ask these really profound questions. Like, can we predict exactly how a brand new material is going to behave, or where a component is going to fail under stress, all without having to do those costly and destructive physical tests? And the answer, more and more, is a resounding yes, and with incredible accuracy. Just take a look at this number, 95%. What does that actually represent? That's the accuracy that a machine learning method, in this case, gradient-boosted trees, achieved when it was predicting the very structure of new complex metal alloys. Being able to know this ahead of time with such high confidence, it's a total game changer for materials science. It just accelerates the discovery of next-gen materials for, well, everything from aerospace to medical implants. And it's not like there's one magic model that does everything. As you can see from this chart, engineers are constantly testing different algorithms to see what works best for a specific problem. Here, when they were trying to predict a key property called the elastic modulus, a model called XGBoost just blows the others out of the water. That R-squared value of over 0.96, that's a statistical way of saying it's incredibly accurate. This is really about finding the right tool for the right predictive job. Okay, so we can create new designs, and we can predict how they'll perform. The final piece of this puzzle is refinement, and that's our third section, using machine learning in the relentless pursuit of the perfect optimized design. So traditionally, optimization is, well, it's a pain. It's a slow process of trial and error. You change one thing to make it stronger, and whoops, now it's heavier. You make it lighter, but now it's weaker. ML-aided methods, on the other hand, can juggle all of these competing goals: cost, weight, strength, emissions, all at the same time, cycling through thousands of possibilities to find that perfect sweet spot. And again, you see this popping up everywhere. Machine learning is optimizing the literal recipe for new alloys using Bayesian methods, which are fantastic for finding the best answer when you don't have a ton of data. It's fine-tuning manufacturing with something called particle swarm optimization, which, get this, is inspired by how birds flock together. And it's perfecting designs using genetic algorithms, which kind of mimic natural selection to evolve better and better solutions. It is an engine for constant improvement. So what does this all mean for the actual engineer? I mean, is the human just getting replaced here? No, not at all. The real story is one of collaboration. It's about a powerful new human-AI partnership. This right here is the single most important takeaway. This new toolbox isn't about making the engineer obsolete. It's about augmenting their intelligence, their intuition, freeing them up from all the tedious calculations so they can focus on the big picture, on creativity, on problem solving. It's really about giving them superpowers. So, to wrap it all up, the modern mechanical engineer now has a virtual draftsman to instantly explore ideas, a crystal ball to predict outcomes, and an optimization engine to refine their work to a degree that was honestly never even possible before. And all of this leaves us with one final powerful thought. You know, for centuries, our tools have been static. We learned how to use them. Now, for the very first time, our tools are learning right alongside us, which really makes you wonder, when our tools can learn, are there any limits to what we can build?